Hello students, today we'll discuss construction of new matrix from old matrix. So take the example, let XD be matrix space, define Dn of xy is equal to d of xy to the power 1 by n, where n belongs to n is fixed. N is natural number. Then we'll show that xdn is matrix space. We'll verify one by one 4 axioms of matrix. So first 3 axioms, positivity axiom, symmetry axiom, are simple examples. Axioms. Triangle inequality is somehow difficult. So M1, since d of xy greater equal 0, as d is a metric, therefore d of xy to the power 1 by n must be greater equal 0, and therefore dn of xy greater equal 0. M2 axiom, d of xy, dn of xy is equal to 0 if and only if d of xy to the power 1 by n is equal to 0. If and only if by taking nth power on both sides we will get d of xy is equal to 0. If and only if x is equal to y, since d is a metric. M3, dn of xy is equal to d of xy to the power 1 by n, but as d is a matrix, so I can write d of xy as d of yx. So this is d of yx to the power 1 by n, and then by definition this is again dn of yx, thus symmetry axiom hold. Triangle inequality. M4, triangle inequality. To show dn of xy less equal dn of xz plus dn of zy, where x, y, z are 3 elements in x. So for this, dn of xy to the power dn 1 by to the power n will become d of xy, and this d of xy is less equal d of xz plus d of zy by triangle inequality for d. And then this is less equal, this is equal to dn of xz to the power n plus dn of zy to the power n. Is it clear? But then this is less equal dn of xz plus dn of zy to the power n. By using binomial theorem, a plus b raised to n is a raised to n plus nc1 a raised to n minus 1b plus nc2 a raised to n minus 2b square plus dot dot up to ncn, that is 1 b raised to n. So by using that, we'll get this to be dn of xz to the power n plus nc1 into this term. This term means if I just take this as a plus b to the power n, this is a and this is b, then this will become a raised to n plus nc1 into a raised to n minus 1b plus nc2 into a raised to n minus 2b square plus dot dot up to b raised to n. Then this is less equal a raised to n plus b raised to n because these terms are positive due to dn of xz and dn of zy are positive. So that intermediate terms will become positive, and this is nothing but dn xz raised to n dn xz raised to n plus dn zy to the power n. But what is this? So this is equal this. This is equal this. So this is less equal this. This is less equal this. This is clear? For that I have explained this. Taking nth root, we get dn of xz is xy is less equal dn of xz plus dn of zy. dn of zy. Thus dn satisfy triangle inequality also. Okay, so dn is metric for x and therefore x dn is metric space. So this is less equal this just by binomial theorem and intermediate terms are positive or non-negative side. So this is the new metric constructed from old one. So only from D for any positive integer n I construct countable number of matrices because set of natural number is countable. Okay. So now we'll take the next example. Second example 2. Let XD be metric space define sigma on X as sigma of xy is equal to d of xy upon say k plus d of xy where k greater than 0 is fixed real number. Then sigma is metric for x. So M1 axiom, sigma of xy is 0 if and only if this is sigma of xy is equal to this must be greater equal 0 because d of xy greater equal 0 and k is positive number. Numerator is positive, denominator is non-negative positive number, therefore it must be greater than 0, and moreover this quotient is defined as k is strictly greater than 0 even though d of xy is 0. So sigma is well defined function. Now sigma of xy is 0 if and only this must be 0. Denominator is positive number, multiplying both sides by k plus d of xy, we get d of xy 0, d is a matrix, therefore d of x is equal to y. Thus positive axiom hold. Again sigma of xy is equal to this. In this, if I interchange x and y, then we'll get it to be sigma of yx. Therefore symmetry axiom also hold. So sigma satisfy M1, M2, M3 axiom. So we have to verify triangle inequality. Triangle inequality is important. So only for those examples we'll verify triangle inequalities now, because first three axioms are too simple. So M4. Now since d of xy less equal d of xz plus d of zy, what this implies is, if I take the reciprocal, 1 upon d of xy greater equal 1 upon d of xz plus d of zy. Firstly, if x is equal to y, then your sigma of xy will become 0. 0 must be less equal sigma of xz plus sigma of zy, because that hold. So for x not equal to y, for x not equal to y, we will take this condition. Then multiplying this by positive number k, I will get this one, since k greater than 0. Again, if you add same number on both sides, I will get this is greater equal 1 plus k upon d of xy greater equal 1 plus k upon dxz plus d of zy. Now this implies is k plus d of xy upon d of xy is greater equal k plus d of xz plus d of zy upon d of xz plus d of zy. Taking that reciprocal, we'll get d of xy is upon k plus d of xy less equal d of xz plus d of zy upon k plus d of xz plus d of zy. This is less equal again. This is equal to d of xz upon same denominator plus d of zy upon same denominator. Okay. So, and then xz upon this denominator plus d of zy upon that same denominator. This is equal to that, and it is again less equal d of xz upon 1k plus d of xz plus d of zy upon k plus d of zy, because in this that denominator is greater equal this denominator. In reciprocal, inequality reverses, and that's why we will get this. Okay, by definition of sigma, we get sigma of xy less equal sigma of xz plus sigma of zy. Thus, sigma satisfies all axioms of metric, and therefore X with that sigma is a metric space. So this is the new metric defined by using old metric. In fact, whatever k value may be, In addition that, if I have some metric D defined on X, then its positive scalar multiple D is a metric, then KD for k greater than 0 is metric. So positive scalar multiple of metric is again a metric. It is too simple to verify that positive scalar multiple of metric is a metric. Similarly, if I have two matrices D1 and D2 defined for set X, then d1 plus d2 of xy is equal to d1 of xy plus d2 of xy is also metric for x. Just by using the metric axioms of d1 d2, you can easily verify that sum of matrix for x is again metric. Positive scalar multiple of metric is again metric. Product of two matrices need not be metric. Product of two matrices need not be metric. How product is not metric? On R, d of xy is equal to mod of x minus y defines metric. Define metric, which is usual metric. Which is usual metric. Then d square of xy, d into d, that is d of xy square, which is equal to x minus y square, is not metric for R. Not metric for R. Justification: for x is equal to 1, y is equal to 2, z is equal to 3, d of xz, d square of xz is equal to 1 minus 3 bracket square, which is equal to 2 square is 4, and d square of xy plus d square of yz is equal to 1 minus 2 bracket square plus 2 minus 3 bracket square. This will become 1 plus 1 is equal to 2. This implies d square of xz is not less than d square of xy plus d square of yz. Triangle inequality fail. And therefore, d square is not metric. So from this we can say that product of two matrices need not be metric. In fact, in first example, I have defined dn of xy is equal to d of xy to the power 1 by nth root of d of xy, where n is positive integer. It defines metric. But if I take dn of xy to be d of xy to the power n, then it is not metric. Then it is not metric. Okay. So up to now, I explained that sum of matrix is a metric scalar, positive scalar multiple of metric is a metric, while negative multiple of metric is not metric because your positive axiom must fail. If d of xy is positive, then minus 2 times d of xy, minus 2d of xy will become minus 2 into d of xy is a negative number, and we required d star of xy is always greater or equal to 0 for any metric d star, and therefore negative scalar multiple or 0 multiple is also not a metric. Is also not a metric.